Have you ever noticed that things change size when they get hot or cold? It's a fascinating phenomenon that affects everything around us. It's a fundamental principle of the universe, and we see it everywhere, from the smallest objects in our homes to the vast landscapes that change with the seasons. Metals, for instance, expand when heated and contract when cooled. This simple yet profound behavior is something we often take for granted. This phenomenon, known as thermal expansion, is a powerful force that shapes our world. It influences the design and function of countless objects and structures. Think about a hot summer day. The heat affects not just us, making us seek shade and cool drinks, but also the very infrastructure around us. Railroad tracks, for example, expand in the heat. This can lead to dangerous buckling if not properly managed. Bridges, too, stretch under the scorching sun. Engineers must account for this expansion to ensure safety and stability. Even the pavement beneath our feet can buckle and crack. This is why you often see road repairs in the summer. These are all examples of thermal expansion in action. It's a constant, invisible force at work in our daily lives. But thermal expansion isn't just about things getting bigger. It's also about the stresses and strains that occur when materials are restricted. When materials are prevented from expanding or contracting, significant forces can build up. These forces can cause serious damage. These forces can be incredibly powerful, enough to shatter glass or tear apart steel. This is why understanding thermal expansion is crucial. So, understanding thermal expansion is not just about science, it's about safety and engineering too. Engineers must design structures to withstand these forces, ensuring they remain safe and functional under varying temperatures. To understand thermal expansion, we need to zoom in to the atomic level. This is where the magic happens, and we can see the fundamental principles at play. Imagine atoms as tiny balls constantly vibrating and jiggling. These tiny movements are happening all the time, even in solid materials. When we heat something up, we give these atoms more energy. This energy makes them vibrate more vigorously, increasing their motion. They vibrate faster and move further apart. This increased distance between atoms is what leads to the expansion of the material. This increased movement is what causes the material to expand. The more energy the atoms have, the more space they need, and thus the material grows in size. Different materials expand at different rates. This is because the atomic structure and the forces holding the atoms together vary from one material to another. This is because the atoms in different materials are held together by different forces. Stronger bonds mean less expansion, while weaker bonds allow for more movement. For example, metals generally expand more than ceramics because the bonds between metal atoms are weaker. This makes metals more responsive to heat. This difference in expansion rates is important for many applications. Engineers and designers must consider these properties when creating devices and structures. For example, we use different materials in a bimetallic strip, which bends when heated because one metal expands more than the other. This bending action is crucial in many mechanical devices. This simple principle is used in thermostats and other temperature-sensitive devices. By understanding thermal expansion, we can create more efficient and reliable technology. Engineers have to carefully consider thermal expansion when designing structures. This phenomenon, where materials expand when heated and contract when cooled, can have significant impacts on the integrity and safety of various constructions. Bridges, buildings, and even sidewalks are designed with expansion joints to accommodate changes in size due to temperature fluctuations. These joints are crucial in preventing structural damage and ensuring longevity. Take bridges, for instance. These massive structures expand and contract significantly with temperature changes. The expansion joints allow the bridge to flex and move without causing any damage to the overall structure. Without expansion joints, the stress could cause the bridge to buckle or even collapse. The joints act as a buffer, absorbing the stress and preventing catastrophic failures. These joints, often filled with flexible materials, allow the bridge to breathe with the heat and cold. The materials used are designed to withstand extreme temperatures and provide the necessary flexibility. Railroad tracks are another example where thermal expansion is crucial. The metal rails expand in the heat and contract in the cold. which can cause significant stress if not properly managed. The gaps you see between rail segments aren't flaws, they're intentional. These gaps are carefully calculated to allow for the expansion and contraction of the metal rails. These gaps allow the rails to expand in the heat without pushing against each other and causing damage. Regular maintenance ensures that these gaps remain effective and safe. Without these gaps, the tracks could buckle under the pressure, leading to derailments. This is why understanding and managing thermal expansion is so critical in engineering. Section 4. Stuck lids and sagging power lines. Everyday encounters with thermal expansion. Thermal expansion isn't just something engineers worry about. We see it in our everyday lives too. Have you ever struggled to open a jar lid that's been in the fridge? That's because the cold temperature caused the metal lid to contract slightly, making it tighter on the glass jar. Running hot water over the lid heats the metal, causing it to expand and loosen the grip. Power lines are another visible example. On hot days, you might notice them sagging lower than usual. This is because the heat causes the metal wires to expand, increasing their length and causing them to sag. In colder weather, the wires contract and become tauter. Section 5. Too hot to handle when thermal expansion poses challenges. While thermal expansion is often manageable, it can also pose significant challenges. In precision engineering, even tiny expansions can be problematic. For example, in microelectronics, thermal expansion can cause components to shift out of alignment, leading to malfunctions. Another area where thermal expansion is a major concern is in space exploration. Spacecraft experience extreme temperature changes from the frigid cold of deep space to the intense heat of atmospheric re-entry. These temperature swings can cause materials to expand and contract dramatically, potentially damaging sensitive equipment. To overcome these challenges, engineers use a variety of techniques, including selecting materials with low thermal expansion coefficients, designing structures to minimize thermal stress, and incorporating active cooling systems. Section 6. Taming the expansion engineering solutions for thermal challenges. Engineers have developed various clever solutions to address the challenges posed by thermal expansion. One common approach is using materials with low coefficients of thermal expansion. These materials, often ceramics or specialized alloys, are less prone to expanding or contracting with temperature changes. Another strategy is designing structures with features that accommodate expansion and contraction. This might involve incorporating expansion joints, as seen in bridges and sidewalks, or using flexible materials that can absorb the stress caused by thermal movement. In some cases, active cooling systems are employed to maintain a stable temperature and prevent excessive thermal expansion. This is particularly important in precision machinery and sensitive electronic equipment.